You thought the series was over, but psych, it's time for part 11. For some reason, terrains in Unity aren't yet officially supported in ShaderGraph. It's been right here in the roadmap for a while now. Since 2021? Oh my god. But thankfully, you can actually sort of handle terrains in ShaderGraph anyway. In this tutorial, I'll show you how, and we'll create a system to automatically place rock on sloped parts of the terrain, and another system for doing a world scan effect which runs over the terrain surface. Oh, and by the way, I've moved to Unity 6 for future videos. Most of what you will see here probably will still work in 2022 LTS, but I just wanted to make that clear here. I've created a basic terrain to work with and drawn 4 texture layers onto it using textures from ambientcg.com. It's not particularly well painted, but it'll do. When I want to recreate something that Unity already does, but slightly differently, my first port of call is usually just checking what they did. In URP, we can scroll down in the project view and find Universal RP Shaders Terrain. There are lots of files here, but the one called terrainlit sounds about right. This is an HLSL shader file, but don't worry, we'll be back in ShaderGraph land very soon. The first thing I'm interested in is the properties block, particularly these ones under Set by Terrain Engine. Actually just these 5, we can worry about the rest some other time. Basic Unity terrains can support 4 texture layers, and the terrain system sends this data to the shader via the first texture, named Control. Each color channel of the texture contains the strength of one of the layers at that point on the terrain, so the red channel is layer 1 strength, green is layer 2, and so on. The values for the 4 color channels should sum to 1, which will be convenient later. Then these 4 textures named Splat 0, Splat 1, etc. are the 4 texture layers themselves. When we scroll down a bit and look at this first pass, Unity likes to separate out the core logic for the pass into a separate file, so I'm going to open the terrainlit_passes.hlsl file, which contains a function called splatmapmix. It's doing a bunch of things, but the main one is at the top here. It's sampling the 4 texture layers. Then at the bottom of the function, it's taking layer 1's texture sample and multiplying by the control texture red value, then adding the layer 2 times control green, and so on. We'll be doing basically the same thing. First, let's create a new graph via create shadergraph urp lit shadergraph and name it something like custom terrain. Once we're in, let's just add all the textures we need. 1 named control, and 4 named Splat 0, Splat 1, and so on. For each of these, we don't actually need them to be exposed to the inspector like usual, since these textures are going to be set directly by the terrain system. So let's select each one and disable Show in Inspector. We should also enable Use Tiling and Offset to make sure that the tiling options on each of our texture layers gets accurately reflected in our terrain. Now is also a good time to go through all these textures and make sure that the reference string exactly matches those used in Unity's own terrain-lit shader, with an underscore at the start and no gap between the word and the number. Let's drag the control texture onto the graph and extract data from it using a sample texture 2D node. By dragging out a wire out of the R, G, B, and A outputs, we can get the weights for each of the 4 texture layers. In fact, we could output this control RGBA directly to base color and visualize the weights directly. We can then drag the Splat 0 texture onto the graph, sample that too, and multiply the control R channel with the Splat 0 RGBA output to get the final color for this texture layer. This layer corresponds to grass for my terrain. Then let's sample Splat 1 and multiply by the control G channel to get the rock amount. Then Splat 2 multiplied by control B for the amount of sand. And finally, Splat 3 multiplied by control A for the amount of snow. Now we have values for each color channel, and we can just add these together and output the result to base color. While editing, I realized you may also want to turn on the smoothness so that the whole terrain isn't super shiny. Going back to the scene view, we can see that the terrain is roughly the same as the original terrain lit shader, just without support for all the things that terrain lit can do, like normal mapping. Next, let's do something more interesting with our terrain layers. When painting terrains, it can be tricky to get something like a rock layer to perfectly line up with the steep slopes of something like a mountain. In those places, it's useful to let the shader automatically detect those slopes and paint on the rock texture for you. First, to help demonstrate this effect, I've reset my terrain layers and drawn on something similar, but just using the grass, snow, and sand layers. I still have the rock texture layer in slot 2, I'm just not painting it onto my terrain. Let's extend the graph to implement our own auto rock painting system. We'll do it by taking the normal vector on the surface of the terrain and checking its y component. If it's around 0, then we're detecting a sloped surface, and if it's close to 1, or -1, then we're detecting nearly flat ground. Let's add two float properties. One for the y component, where we start detecting a rock face with default value 0.5, and another for where the rock face ends, with a default of 0.6. We can make them both slider types with a range of 0 to 1. Let's use a normal vector node and use a split node to grab the y component, and then feed that into the in slot of a smooth step node. I've used this before, but to recap, when we input something to smooth step and it's less than the edge 1 input, then the node outputs 0. If it's more than edge 2, the node outputs 1, and if it's between those edge values, then the output is a smooth curve from 0 to 1. When we plug the normal start and normal end values into the edge inputs, then you'll see on the node preview that the vertical parts of the sphere are black. Those are the cliffs, and the flatter parts up top are white. We don't need to worry about the lower half of the sphere being all black, because in a real Unity terrain, nothing will have a negative normal y value. Let's leave ourselves a bit of space by moving a few nodes around for this next step. Instead of just feeding the Splat 0 grass texture sample into this first multiply node, I'm going to use a lerp node to pick between it and the Splat 1 rock texture, based on the result of that smooth step node. The rock texture needs to go into the E slot and the grass texture in the B slot, and then we can feed the lerp result into the multiply. If we go into the scene view and play around with the normal start and normal end values, we'll see the rocks appearing on those sheer cliff faces. Nice! I'd like to add one more effect into this custom terrain shader, and that's a world scan effect. I recently built a new PC, and to test out how well my rig runs, I gave No Man's Sky a go. On my old build, it would take, no exaggeration, over 10 minutes to load, and it would stutter like mad once I got into the game. But with my new machine, which I've affectionately named Goose PC, it's close to about 10 seconds, and it runs smooth as butter. This is a bit of a digression, but it did help me remember that I'm a fan of these kinds of world scan effects that you see in a fair few open world games. Let's hop back into our graph. I'll add 4 properties. One will be the scan color, which I can set to HDR mode so that we can use bright emissive colors. Let's set the default to some nice blue and ramp up the emissive intensity a bit. The next is the scan origin, a vector 3 which represents the point in world space where the scan will start expanding from. Then a scan width float, which is the thickness of the scan line in world space units. And finally, a scan distance, a float which is how far the scan has traveled so far. For each of these, I like to change the reference value so that there's an underscore at the start and no underscores between words, like Unity uses for its standard shaders. Essentially, if a terrain pixel is further than the scan distance, but less than the scan distance plus scan width away from the scan origin, we can output scan color as an emissive color. For that, we can use 2 step functions, like so. First, we can get the distance by feeding the scan origin and the position in world space into a distance node, and then use a step node with this in the in slot and scan distance in the edge slot. To recap, This will output black for everything under scan distance and 1 for everything above it. Then add the scan distance and scan width together and use them in a second step node edge slot. When we 1 minus the result, everything under scan distance plus scan width will be all white, and everything further than that is black. If we multiply the two values, we get a white ring representing the scan line. We can then multiply by the scan color and output the result to the emissive block on the output stack. If you remember, emissive colors show up regardless of whether the object is in shadow, and combined with a bloom filter, they will glow if the intensity is above the bloom threshold. When I play around with the values in the Materials Inspector window, we can see the scan working as expected, but really, I want to drive this with C# scripting. Unity provides a way to send values to shaders within a script. This isn't a C# tutorial per se, so here's a script I whipped up beforehand. We take in the terrain, and in start, we get a reference to its material. In update, I'm going to raycast using a mouse click and set the scan origin point to the raycast hit point. We can do this via the setVector method on the material, which takes in a string, which should be exactly equal to the reference value we set in ShaderGraph, hence why I like to use the same format for all reference values, with an underscore only at the start, and the vector3, which we want to send to the shader. But then I can also increase the scan distance over time using a speed value I feed into the script via the inspector. To send it to the shader, I'll use the setFloat method. As you might have guessed, there is a set method for all the types you can think of: colors and integers and matrices and textures. Now when we return to the scene view and attach the script to a game object in our hierarchy, set up the parameters on the script, and go into play mode, we can click on our terrain and see the world scan spread across our special terrain, which is still automatically calculating rocky cliffs. I hope this video was helpful. I want to know what kind of shaders you're interested in me covering on this channel in the future, so I'm running a poll at the moment to ask for your feedback. I'm giving away a handful of keys to my shader packs to a few lucky participants. I've already sent out a few, but I'll keep the poll open for a while and select a few more winners in a couple of weeks. If you already filled in the poll, thank you so much. I have a few new ideas for videos thanks to you. Until next time, have fun making shaders.